Okay, so let's go and see where we are. We are going towards RMI. That's what we need to know for your next assignment. But I want to first lay down the foundational concepts in IPC for RMI. Okay, so everything I've talked about applies to both RMI and non-RMI systems. Okay, I haven't even talked about anything that's specific to RMI. Okay, so now let's go and talk about some issues, not all, that separate IPC mechanisms. So far I've looked at concepts that unite them, and now let's look at issues that divide them. Okay, and there are many such issues. We kind of reference one of them: do you block or do you not block? Are you using a blocking queue or not a blocking queue? Okay, but from the big issue to introduce RMI is this. It's the general model of IPC. So RMI stands for Remote Method Invocation. Method is a special kind of procedure, a procedure that is associated with an object we call a method. Okay, so the more general concept is remote procedure call. So before we look at RMI, we're going to look at remote procedure calls. Remote procedure calls are a form of message passing. So they are different from whatever is not remote procedure call. And you can talk of that as data communication, or I'm going to call that remote assignment. Okay, so these are the terms I'm going to use. And before I start defining them, let's try to go and see what they might mean to you. Okay, so based on the wording, what could be the difference? Okay, and this is hopefully not a very hard question, but it's good to think about this before we actually study a remote procedure call. Okay, so that's the next question. Okay, so as you guys mentioned, in one case, RPC is a layer above remote assignment. Okay, and RPC is aware of the fact that you're actually trying to invoke a procedure at the other end, whereas remote assignment is not aware of the fact that you're trying to execute a procedure at the other end. Okay, and why do I call it remote assignment? The message is, what are we doing? What is the effect of sending and receiving a matching pair of sending and receives of a message? Okay, the effect is to essentially remotely assign to a variable a value. Okay, so we assume that there is a variable at the other end, which is typically called a buffer. Okay, and we assume the message that you send is an expression, is a serialization of an expression to be assigned to that variable. Okay, so that expression travels from the client, from the sending process to the receiving process, and once it's consumed in the receiving process, it's assigned to this variable. Okay, so that is the abstraction many IPC mechanisms provide. Okay, that you read a value into a buffer, a value that you sent from another end. Okay, so the result of a matching send receive is to assign a sent expression to some variable, typically called buffer in the remote processor thread. You can talk of this stuff happening both between threads and between processes. Okay, and to make this very apparent, I'm going to use a very, very old language and some interesting syntax. So type of expression, you might just allow strings to be sent, you might allow arbitrary data types to be sent. That's an orthogonal issue. Okay, but languages have differed based on what types they allow to be sent this way. Okay. So here's a language called CSP. In CSP, there are processes talk to each other directly, and one process can name another process. So the sending, and so there's a distributed port, as I said, this distributed queue connecting the two processes, and P1 names the port by using P2's name, and P2, and so the sending process names the port by using the receiver's name. Okay, so P2. So you're saying here, send to the port named by P2 the value of the expression E1 plus E2. Okay, and at the other end you say receive from P1. Okay, we're talking the same port, we're just giving different names to it, a value that is assigned to the sum variable. Okay, so when the matching send and receive occur, E1 plus E2 in process P2 is assigned to a sum in process P1. Okay, so they're talking of the same queue, they're just giving different names to it. Okay, we assume here that each process knows the ID of another process. This is really meant for within a particular computer. In fact, this is really meant for multiple threads within a particular process. But this will translate to also multiple processes that are on a host. And it is something that CSP supported. And how many of you have heard of communicating sequential processes or CSP? How many of you have heard of Go? Now you're all excited. Okay? So this is exactly, if you go and look up Go, Go provides this form of communication, a variation of this communication inspired by CSP. Okay? And you would think that, it's an old fashioned that's come alive again. But when CSP came out, it was a modern language for a bunch of researchers working on Unix. And those same researchers happen to be at Google right now. And they are the researchers who created Go. Okay? So that's probably the reason why they know about CSP. Okay? But the general idea is that you have expressions being assigned to variables. And the same concept arises in sockets, whether they're provided directly in Unix or through Java. And so in Java, you can say outstream.println E1 plus E2, where outstream is connected to some socket. Okay, it's a stream created from a socket rather than from a file or from the standard input. And at the other end, you can say a variable is assigned instream.read, and instream and outstream are two local names for the same port. Just as P1 and P2 were two local names for the same abstract port, instream and outstream are two names for the same port. Okay, so this is remote assignment. What I'm calling remote assignment, this is a term that I don't know anybody else uses or not, but it is, you can call it data communication. And you can see why I call it remote assignment. CSP was the first language I read about when I was studying interprocess communication. So obviously I am also very influenced by it. Okay, it is probably the first language that did invent this idea. Okay, when I looked at the survey of these languages. Okay, so in Java you have this outstream and instream as I mentioned. So what happens in RPC? In RPC we say at the remote end. So the RPC mechanism knows about not some variable at the remote end, but some method at the remote end. Okay, and the purpose of communication is to call this method remotely from another process. So in local invocation, some code within a process calls a method within the same process. Okay, so the caller and callee are in the same process. Now the caller and callee are in different processes, just as in the previous slide, the expression and the variable were in different processes. Okay, so message is now what you're putting in the queue is a request to invoke a method. Okay, remotely. That's what you're putting in the queue. The queue, like I said, can have an arbitrary data object put in it. And here we assume that the queue has a request to invoke this method. Okay, so when that message can be put into the queue, and when it's consumed, the effect of consuming the message, the effect implemented by the RPC mechanism directly, not by some higher level layer. Okay, you can simulate remote assignment. You can build RPC over remote assignment, as you guys have hinted. You can build remote assignment on top of RPC. There are systems that have implemented RPC directly on top of TCP/IP without having a socket layer underneath, or directly on top of UDP. Okay, there are implementations that are very efficient that have done that. So typically, indeed, like you guys mentioned, remote assignment is a lower level layer, but the IPC mechanism itself knows about this method and calls it when the message is consumed. Okay, so that's RPC. So the result of send is to invoke some operation on the remote receiving thread or process. Again, these kind of mechanisms started off as inter-thread communication. Threads were called processes because processes didn't have any sub-threads in them at those times. Now that processes have many threads within them, things are different. Okay. So usually built on top of data communication, but not necessarily. It doesn't have to be that way. Okay. So if you have a method called status or called print, okay, that takes as an argument some string to be printed. Okay, I know we are out of time, but I'll take 30 more seconds. Then what you can do is and we'll talk about this in great depth next time. You can have a call like this, which is what was provided by a system, Sun RPC, and which was tied to C. Or we can have a call like this, which is the kind of call that you support in Java. Okay, they're both examples of RPC, and this is Java RMI. Okay, so they're both and so this gives you a concrete feel for what an RPC system might look like, and how it might differ from a data communication system that some of you have used in 431. Okay, so why plural port? I say distributed queue of ports. The communication often results have to go back in the other direction. So we're talking of two queues: one queue receiving requests at the callee side, and one queue receiving the results, return messages at the calling site. Okay, so we just bundle them into one picture, but they're really multiple queues. Okay. 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 So last time we saw that an IPC mechanism can be distinguished by whether it does data communication or what I call remote assignment, okay, which is inspired by CSP language, which I mentioned was the basis for the Go language, or it can be done via remote procedure call. And in remote assignment, you're sending data or expressions that get assigned to buffers or variables at the other end. Okay. In remote procedure call, what you're depositing in the queue, in the distributed queue, is requests for services. Okay. And so it's some encoding of a request, and that's what the caller, that's what the sender does, and the receiver is expected to take that request and in response to it execute some procedure, and if there are any results, send this result back, which the sender can then go and get as a return value of the called method. Okay. So I showed you two examples last time. One was Sun RPC, which was designed for the C programming language, and the other is Java RMI, which is the remote method invocation. Okay, Java remote method invocation. So let's look at the two alternatives, the Sun RPC and the Java RMI alternatives, and let's go and try to, based on what you can understand. We really don't know what these calls are doing. Okay, they're both calls in two different languages, and based on what you see there, can you point out a difference without really understanding them completely? You can probably see some differences. Okay, so what's the differences? Okay, and there's an obvious difference. Source code of Sun RPC is distribution and location aware. Okay, so it's location aware. You can see that it's got the host argument there. So if it's location aware, it must also be distribution aware. Okay, and the source code of Java RMI call is not, I meant to put unaware here, is not distribution and location aware. Okay, so that's something you can see from just looking at the term host. In one place we see host, and the other place we don't see host. If we don't understand anything else, we understand at least what is lacking in one and what's present in the other. So my question to you right now then, so this really means that some other code in Java RMI has this awareness. Okay, what that piece of code is, we'll see it either later today or next time. Okay. So my question to you is, which is somewhat recapping the idea of location awareness, but let's recap it and be more specific. What you can also see that you have to type more in the Sun RPC case and type less in the RMI case. But assuming that's not a problem, typing more or less, typing more. What is another advantage of making the source code of the call? We don't know what happens to the compiled code right now. Okay, that we'll talk about later. But what is the advantage of making the source code of RMI distribution or location unaware? Okay, what's the tangible benefit, assuming you're willing to type more? Okay, in the Sun RPC case. So as David mentioned, you can direct the local procedure call to a arbitrary host in the location unaware case, and you have to choose the host in the location aware host case. But there's even a more subtle advantage. The call can be made locally in the location unaware case, okay? Because it doesn't say, you don't see from there, that call that you see there is the same syntax as you would use for a local call. So you could make it locally, you could make it to an arbitrary host. So you can imagine the service first residing in your process. This, by the way, typically has happened in programs we've developed. We develop it all in one process, one machine. Then we go and say, hey, this can be distributed. So we go and take a piece of code and put it in another process. And the user of that piece of code doesn't have to change if that piece of code was location unaware. Okay? So that's a tangible benefit that the less information you put, the less you commit in some sense. Okay? And that's a source code. So, like I said earlier, other components of the calling process may be location and distribution aware. So it doesn't mean that the client is location and distribution aware. The client or the caller can be aware, and it's just the call we're talking about. Okay. So now I'm going to ask, what is the advantage of making the compiled code of call distribution unaware? Okay, not the source code, but even the compiled code. Okay, so I'm saying the compiler doesn't know that this call is remote or local. In one case, the programmer didn't know. The programmer wrote this, but the compiler could do some magic underneath. And now I'm saying the compiler also doesn't know when processing that call. The compiler could be distribution aware in general. There can be other parts of the language I haven't told you that require the compiler to be aware of the fact that that code can be executed distributed at a remote location. Okay, but the compiler, when it looks at just that piece of call, doesn't know whether it's distributed or local or where it's going. So what's the advantage of making the compiled code of the call distribution unaware? So as I mentioned, if a compiler makes a decision, then that decision is made at compile time. Okay, and so what Jason inferred from that was that if you allow the compiler to be unaware of this particular the location, then the decision of where to go, which host to go to, and more importantly, whether to go local or remote, can be made dynamically. It doesn't have to be made at compile time. Okay. So there's this whole notion of binding. When do you bind yourself to a particular decision? When do you commit to some decision? And you can commit to the decision later. Okay. This may make your execution slower. Okay, that's generally a trade-off between late binding or late commitment, and so late commitment often means more flexibility, but it also means sometimes slower runtime. Okay, so that's an advantage here. Okay, and in fact, all RPC systems I know that support distribution through the programming language make sure that the call is dynamic, is actually location unaware. Both the source code and the compiled code is location unaware. Okay. Okay, so now that we understand when decisions are made, let's try to understand what's happening. Okay, so what exactly needs to be sent on the wire when a RPC call is made and when it terminates? Okay, that's the next question. And some of you kind of hinted about what happened, or at least hinted that you know what happened, because you said RPC system can be built on top of a data communication system. A data communication system can be used to simulate an RPC system. So for simulation, you need to go and send some data across the network, right? So my question is, when you make a call, what kind of data has to go to the caller and come back from the caller? Okay. So nature of call initiation and termination data deposited in queues. There's two queues actually. There's a queue that's going to that the callee goes and processes, and there's also information being returned back and that is a queue processed, consumed by the caller. Okay. Okay, you guys pretty much have got everything. So John Ray mentioned that you want to send the procedure name. You need to send some identification for the procedure. Okay. There are three terms I'll use interchangeably, but they really have different meanings. I'll use the word method for something that can return a value or not return a value. Something that returns a value we'll call a function, and something that doesn't return a value we'll call procedure. Okay, but sometimes I'll use these terms interchangeably. Okay, and usually methods are operations invoked on objects, and so there's no real good term to combine function and procedure in non-object-oriented language. So I might use the word method. Okay, so method ID only if there are multiple methods per port. If you're calling only one procedure or one method on that port, then you needn't go and send the method ID each time. It's implied. Okay, but usually you do have multiple operations being serviced on the same port. Okay, so if there's a separate queue for each method, then you don't have to send the method ID. Okay, that's implied at the other end. At connection time, we can go and establish which procedure we are calling. Okay, we do need to send the parameter values. Okay. And also, if you're going to get results back, and if we haven't gone and done some handshaking earlier, we need to go and tell the receiver how to go and send information back to us. Okay, a return address we want. And those of you who've seen studied networking, you know that happens, that you go and often send the return a return location. Okay, so caller info if such information has to be sent per call. And then there is some data that has to be sent back on termination. Method status if desired. Okay, it's possible that you will call a procedure at the remote side. You don't want to wait for any results back, and you don't care whether it executes or not. Okay, you're a sensor. You're sending data. You're sending data periodically. If some data, some information gets lost, who cares? Okay, you don't want to wait. So, and if you're calling a function, a procedure which doesn't return a result, you may not wait for. You don't have to wait for the result. But if there's a result, then you probably want to wait. So you get results back, and you might want to go and indicate also which call that result corresponds to. Okay, if the receiver, if the caller is waiting for a particular call, then you don't send that, because after each call it's waiting for the return value, so it knows what call that return value is for. It might go and make a bunch of calls and then wait for all the data, in which case and the return values may come out of order, so in which case it needs to match its call with the return value also. Okay, so there may be some call ID also sent back. Okay, so let's try to understand this even better by going and comparing what happens in a local call to what happens in a remote call. Okay, if any of you has done a compiler course, you really know what happens in a local call. But from just using a programming language and studying and doing computer 411, you do know a little bit of what happens when you make a local procedure call. And we've talked about that also in the context of threads. So what's happening is that there's a calling process. The calling process is in some procedure, some local procedure. That procedure is on the stack of that particular process or thread. Okay, and it's going to make now a call. There are two cases: the call is local or the call is remote. Okay, let's consider what happens when that procedure makes a local call. Okay, in that case, you will push another record on top. Okay, you will go and jump to a particular address. The parameters will be processed, the return value will be put on the stack, and the record gets popped. Okay, so you guys study stacks and data structures, and we see that work at work in programming languages. Okay, that's what happens in a local call. Now the question is, how do the steps differ in a remote call? Okay. Again, there is some procedure in a particular calling process that is going to make a call. Previously, when it made a call, an activation record got pushed on top. Now we want to make a remote call. and we want to get results back. Okay, so what should happen? And ideally, we want to consider the case where the compiled code is also location unaware. Okay, if it's location unaware, things should be uniform with what happened in the local case to some degree. Okay, so let's talk about, in general terms or specific terms, how the steps change in a remote call, and what steps remain the same, if any. Okay, so we have two parties here that we have to worry about, two stacks to worry about. Okay, and we have the calling record, and as Brian mentioned, since the compiler is location unaware, distribution unaware, it is going to push some record or the other on top. Okay, what record it pushes could be dynamically decided by some other piece of code, but it is going to push a record. Okay, so it pushes a record, and that can go and call other routines too. Okay, as David was kind of suggesting. But assume that we are doing it all in this routine. This routine doesn't really do the computation. Okay, it is just a proxy or a stub for a remote call. Okay, so it can't do the real thing. The real service that is requested is not done by this. Okay, when you're making a remote call. Okay, when you're making a remote call, you're just asking it to forward the parameters from the activation record to a remote location. Okay, so it's a forwarder or a proxy. So it goes and sends the information that we talked about on the network. Okay, and that information is received. And in response to receiving that information, the calling system, the called system is going to push a copy of that activation record essentially on the remote site. Okay, so the activation record that was pushed, a copy of it is going and pushed at the remote end. Okay, and it's not quite a copy because the return addresses are different. The addresses to which you're jumped and the addresses to which you return are different, but at least the parameters are copied. Okay, and the address from the left activation record is converted into a method ID, which is then converted into another address at the remote end. So you go from a stub address, a proxy address, to a real procedure address at the other end. Okay, and that's going to return and have a result, and that result is then sent back, and on receipt of that message, this activation record is popped. Okay, and the result comes back. Okay, so last time John Ray mentioned the term marshalling and unmarshalling. Okay, and it's interesting this term is still being used. The very first PhD thesis I ever read in my life was the PhD thesis called Remote Procedure Call. Okay, it was by a guy called Bruce Nelson from CMU. And this is where I saw this picture first that I'm talking about. It might have been earlier. I believe it was a thesis done in the 80s. Okay, and I read the term marshalling and unmarshalling in that thesis, and it's interesting. It's still being used. So what is marshalling? I said that the remote activation record is a copy of the local one. Not quite a copy, but almost a copy, modulo the address issues. So copying the local activation record onto a network representation is called marshalling. Okay, copying the network representation into the received network representation into a received activation record is unmarshalling. Okay, and then copying the return value back on the network is called again marshalling. And copying network value back to the received network value to a local return value is unmarshalling again. Okay, so so this is marshalling and unmarshalling. So in RPC, a local procedure call results in just a local call, and a remote procedure call results also in marshalling and unmarshalling of data. And as to repeat what Brian said, a local activation record must always be pushed to support location transparency in compiled call code. But even in code that is source aware of location, a local call is made. Okay, so Sun RPC, that call RPC that we saw, is also a local call made, even though it is location aware. Okay, so you can imagine a system where a local activation record is not pushed. Okay, everything happens inline through some compiler generated code. But I don't know of a system that does that. A local call is always pushed. Okay. So a question at this point is, how is unmarshalling and marshalling different from serialization and deserialization that I talked about earlier? Okay. We talked about an object being serialized onto the network. We talked about little Indian, big Indian values. And now I'm using another term, marshalling and unmarshalling, and they seem similar. In both cases, we are converting to and from a network representation. So based on what you've heard from me or what you know through intuition, what do you think is the difference between the two? Okay, so as David said, marshalling is serialization of activation record data. Okay, the term marshalling came first. Okay, and marshalling is tied to RPC, and marshalization is serialization of RPC data. Serialization is independent of RPC. Okay, and marshalling implies serialization, but not vice versa. Okay, so historically, what happened was that people were doing this remote procedure call. So type data was sent only as part of remote procedure call. There was no notion of sending typed data on data ports as data communication. Okay, whenever you sent typed data, it was as parameters of method calls and return values of method calls. So you did this kind of conversion only during method calls. And as far as I know, Java is the first language that said, yeah, this is a facility that's needed for method calls, but why not also have typed data be sent on data ports? Okay. So they did serialization and deserialization as a lower level abstraction, and marshalling and unmarshalling just use that abstraction because we have now two layers rather than one layer that did both things. Okay. So Java is, like I said, probably the first system to provide serialization as independent layer below RPC. There might have been other systems that I'm not aware of. Okay, but just historically, that's where I first saw it. Okay. So let's try to understand this marshalling through examples. So when I do a call RPC in Sun RPC, that's really a library routine, and that is my local proxy call. Okay, that is what I pushed on top of the caller's activation procedure, and that went and sent the data across through other calls, perhaps. Okay, and you can have in the Sun RPC some method at the remote end that actually does the job, and so that's a remote procedure, and this we will call as the proxy or stub procedure. Okay, stub because it's kind of it doesn't really do the work. Okay, it's a forwarder, and in RMI, the printer.print is now again a stub procedure in a stub object. Okay, so since this is an object-oriented language, we not only have a stub procedure, every procedure is executed as part of some object. So there's a real object at the other end on which you want to invoke a method, and you have a stub or proxy object at the local end in which you call the procedure. Okay, and based on whether when you go and say printer.print the printer may be assigned a real object or a proxy object. Okay, that is determined dynamically. The compiler just goes and calls the print method in one or the other. When printer is assigned a real object, the real method gets called. When printer is assigned a proxy object, the proxy method gets called, and that method goes and does the forwarding and gets the results back. Okay. Okay, so we have, again, we now have not only a remote procedure, but a remote object and procedure. And we now only have, not only have a proxy or stub procedure, but also a proxy stub object in addition. And again, as far as I know, Java is the first language to have object-oriented remote procedure calls. Before that, C++ was very popular. And for C++, there was a system called Corba, which was language independent. So maybe Corba was the first object-oriented RPC system, but that was not really based on any language. And Java was the first language in which such a concept was built in. Okay? But I'm sure a lot of concepts in Java came from Corba. So to understand this even better, now that we know what information is sent across the network and we also understand what marshalling and unmarshalling are, let's go and actually see how this simulation of a remote procedure call can occur over a data port. Okay, so we are trying to convert a data port into a remote procedure call port. Okay, we want to convert remote assignments into, we want to convert remote procedure calls into remote assignments. So what we're going to do is we are going to have at the remote end, so what we want to simulate is a method, a process which has a method and some parameters that are called. But what we have are, what we're going to have, what we have are variables to which values can be assigned. So we're going to have one variable that holds the method identification and some variables that hold the parameters. Okay. So when somebody wants to invoke a procedure call, they're going to go and send expressions. Okay, that's what we can send, but what we want to really send at a higher level is a procedure call. So we'll go and send the method and parameters as separate messages, separate expressions, not as one expression to be put in one item of the queue. Okay, so these will be different items in the same queue. And these two different values get put in the queue, get retrieved from the queue, and they get assigned to the corresponding remote variables one by one. And then the receiving process can, once it receives all the data it expects, it can then go and call the method. Okay, so that's pretty much what happens in the systems I talked about. Sun RPC system is built on top of a data communication layer. So is RMI. I know Sun RPC could go on top of either UDP or TCP/IP, from what I remember, and probably RMI also has that flexibility. Okay. So to understand this even better, let's look at the lower level abstraction, Sun RPC, and try to understand what the different parameters of call RPC really mean. Okay. To understand what's really going on, let's go and see the library in more depth. Okay. So there's a Sun RPC library with these calls, and you can see now what these what these calls expect. So register RPC is a call that is made at the call site, which goes and says, here's a program number, here's a version number. It makes a binding between, it binds a procedure address to a program number, a version number, a procedure number. Okay, an in procedure and an out procedure. So it's saying basically that the procedure number is like the server name. Okay, so the procedure number could be print, or it could be file system, it could be various different kind of services, and they have different that run on a host. So the program number distinguishes among different services. Okay, the version number distinguishes among different versions of it, and as was mentioned, that it could be different versions that do almost the same thing but in a different way, or it could be historically different versions. Okay, and procedure number is an ID that is unique to a particular version for that procedure address. and then you give two procedures, one to serialize and one to deserialize. Okay, so it's saying that my parameters are deserialized by my in procedure, and my result is serialized by the out procedure. Sun RPC expected these procedures to have exactly one argument. Okay, so there's only one in procedure. There's only one parameter expected. You can't have multiple parameters. Okay, so that's what happens at the call site. The call site makes a bunch of register RPC calls. It might have different kinds of procedures in the same service. Okay, if it's a math server, it might have add, subtract. Okay, if it's a counter, it might have increment and get value. Okay, and after you register all the procedures at that particular that is serviced by a particular process, this is what a process is doing. Okay, it goes and calls a method called SVC run, saying, okay, now listen for requests for services I provide. Okay, so you go and register a bunch of services, and then you listen for messages. Okay, the calling site, you go and give host, program number, version number, procedure number, in procedure, okay, which is how to go and send data out. Okay, then you give the actual value to be sent out. Okay, that's the in, and you typically give an address. Okay, and then you give a procedure to go and get results back. Okay, deserialize the results, and you give a variable to get the results. Okay, that's why I show sort of an address there. Okay, so that's what the syntax is. And rather than looking at the print case, because we don't know how to go and implement print, let's look at add, which we all know how to implement. Okay, so there's a callee and there's a caller site. Okay, they both have to agree on some interfaces, right? You have to agree on some header information. If it's add, you have to agree on whether the add is going to take doubles or ints and in what order the parameters sent. So there's going to be some common code. That common code can consist of some interfaces, like I mentioned, and it also consists of some common serialization, deserialization routines. You can't have the same data serialized in one way and deserialized another way. So you really want a common set of routines, and in fact you want the same routine to be used both for serialization and deserialization. Okay, so when it's serializing, it does the serialization. When the system is deserializing, it does deserialization. And as it turns out, you can write the same piece of code to do both. Okay, so there's a common set of XDR routines that both sites share. Okay, so I mentioned that we want to do add. Add normally takes two arguments, but I mentioned that remote procedure calls take only one argument. But that argument doesn't have to be a primitive atomic value. It can be a structure. Okay, so what we'll do is we'll say add goes and takes as an argument a struct in C, and we are going to, the two fields of the struct will be the two arguments, and it's going to go and return the sum of the two fields. Okay, so if you're familiar with C syntax, this is obvious. If you're not, all we're doing is taking a struct and mentioning the fields, and it's like sending an object and you're going accessing the variables of the object. Okay, that struct better be defined in some common interface. So this is my struct definition, and I'm saying this add takes an int as the first argument and a float as the second argument. Okay, and returns a float. So that's my common interface. Here's my XDR routines. Okay, so I need to go and send this S out. I want to receive S back. And you see, I've written one piece of code to do both. XDR int and XDR float are some primitive values that are provided by the XDR package. And when you're in the deserialization mode, it reads whatever is in a stream into a variable, okay, which is the second argument. And so it's saying, okay, read whatever has come into the variable, into the field 1 variable of arg, okay, and read the second thing into the field variable, field 2 F2 field of arg. When you're in the serialization mode, it says, okay, write what is in arg F1 to the stream, and then write what is in F2 to the stream. Okay, so the same piece of code will work for both, because there's a global variable that decides whether you're serializing or deserializing, and xdr int will either go and output a value or input a value, and all we are saying is in what order things should go. Okay, so you can actually use the same routines for both. And this may not make very much sense to you at this point. It should make some sense. But if you do the serialization assignment, it will make a lot of sense. Okay. But the point is, this is how you achieve consistency of serialization and deserialization. So after you make that, after you've gone and implemented add, you will go and register the add procedure. And let's say that's the only procedure that you register. Then you do SVC run in a loop. Okay. And we are using some named constants. So we'll say that we are program number 1 for our host, and we have only one version, so version number 0, and we have only one add method, so we'll just go and give it the number 0. Okay. So this is again some a value that both server and receiver have to agree on. And the caller goes and constructs a value of type S. Okay, because it's going to have to pass it to the remote server. It goes and then does a call RPC, and it gives S as an argument to this call RPC, and it also goes and uses the named constants that have been declared by the server, by the callee. It passes them to call RPC. It passes XDRS and XDR float, and register RPC also had XDRS and XDR float, so that we make sure that S is serialized and deserialized using the same routine, and as is the float. Okay, so we make sure that there's consistency of serialization and deserialization. Okay. Randy's a little puzzled here. Okay, so this is the procedure or scope. Okay, you're just basically saying, think of a particular programming language. You often have a scope, so you're generally saying, here's my scope, here's that host, here's that server, here's that version. Okay, here's the operation ID. This is the ID that I want to go and send. We are sending an ID rather than address. Here is my parameter serializer. Here is my single parameter after that. It's not quite pointing at the right location. It should be a little right of that. Here is my result deserializer. And here's the variable to get the result. And same scope, same operation ID to make sure that they correspond. This is my address. This is the actual procedure to call when that ID is received. Okay, which we didn't do. This is information we did not put in call RPC, because that is decided by the server. And here's my parameter deserializer, which better be the same as the parameter serializer. Here's my parameterized deserializer, which better be same as the result deserializer. And register RPC will call that method, get the value from the stack, send it out, serialize it using the XDR float, and it will be received. Okay, so you get some idea of what really happens in a remote procedure call through this picture. Okay. And to show this a little bit show it in more depth. So let's go and see what happens in call RPC, register RPC, and SVC run. What we're doing is we're going to actually have a data port underneath. So we're going to get or create and then connect, if we haven't already connected, to some data port. Okay, if it's the first call, we'll do that. If it's already connected, we'll just use the previous connection. And we will then go and send our values to that port using the serializer that has been given. And we'll go and receive the value after that using the deserializer that has been given. And at the callee end, we're going to do a registration. Some local tables are going to change, where we go and bind a procedure address with the version number and procedure number. And we bind it with XDR arg and XDR result. And then we're going to again create a port at the other end of the port. Okay. And SVC run, whenever a message comes in, it extracts from the message the version number, procedure number, the argument sent. Okay. Also, it extracts this information for a particular program. We're assuming that some system looked at the program number and decided that this is the process that will go and receive the message. So we don't have to get the procedure number, because that process number or program number, because that was received by the operating system, and we are talking about the process, a specific process right now, and that corresponds to that program number. And it's going to go and look up the procedure address and the XDR routines based on what was received. Okay, the version number and procedure number. So it knows what its serializer to use and what deserializer to use. And it's going to then execute the procedure after serializing and so forth, get the result back, use the XDR routines to send the data back, and go across the network. Okay, so I'm saying the same information I said earlier in a different way, but you see what you have to do, that you have to maintain some data structures at the server end, at the called end, to go and bind what is received on the network to the local address and local XDR routines. Okay, this system allows customization of serialization and deserialization, because this is a library routine. It doesn't understand C types. It doesn't know this is struct S. It just knows that here's a pointer that points to some data structure. So it doesn't know that S is decomposed into F1 and F2. So the XDR routines are the ones that will take that address and go and decompose into F1 and F2 and do the serialization, deserialization. Okay, that work doesn't have to be done in Java, because Java is built into the language. It knows what type it is. It can go and find out what the instance variables are and go and recursively serialize them and deserialize them. Okay. I see some understanding, some confusion in your faces, which is okay. Okay, this is C. This is low level. But those of you who've done operating systems, this should be a little bit more familiar. Okay. So what happens in SVC run is you service a call and then you wait for another call, and do that in a loop. Okay, so that's why I said this is a loop. And again, one of the assignments will have you actually implement marshalling and unmarshalling, and you'll get a little bit an idea of what's happening underneath. Okay. And the reason I'm giving you these details right now is that you're going to be using RPC, and it's very hard to go and understand an API if you don't know anything about how it's implemented. Okay, so you at least have some idea of how RPC is implemented through this picture. Okay. So RPC summary. We can either be doing this should be assignment or remote procedure call. And in RPC, we talk about remote procedure call. Okay. And we can have our calls be location and unaware or aware. And we can talk of this happening in the in the source code or compiled code. And what you get from lack of awareness is the ability to go and choose the location and ability to determine whether it's the code is invoked locally or remotely. Okay, and if the compiled code is unaware, then you have this decision being made dynamically. And the big lesson from all the details I showed you is that there is a proxy method or proxy procedure called at the local end. Okay, that goes and forwards the parameters to the remote end and gets back the result. Okay, and so there's marshalling and unmarshalling. And there is an RPC system at the call side that goes and invokes the right method in response to what is received on the network, and pushes the activation record of the procedure that is called and pops it off and unmarshals the results back. Okay, so these are the things that I want to really bring out in this discussion. Everything else was sort of details to illustrate this.